interlayer modulation of Burnside for advanced energy storage. So I'm going to give my talk following this outline. So first, I will give a brief introduction. So now we are trying to use more and more this renewable and clean energy to replace these fossil fuels, because the fossil fuels is going to be exhausted in the future, and we will need more and more energy storage devices to help us fully utilize these renewable energies. Therefore, to build our smart city in the future, this large-scale energy storage is very, very important. And nowadays, we know that lithium-ion batteries have been widely used in these consumable electronics like the handphones and the laptops. And it also started to be used in the electric bicycles and electrical vehicles. And it could be used in the smart grids in the future. But when we are producing more and more lithium-ion batteries, we are facing a problem. That is, the lithium source is actually limited and unevenly distributed on Earth. So if more and more lithium batteries are produced, the lithium source is going to be exhausted in the future. So we are looking for some other materials that can make the batteries more sustainable. And we see that sodium-ion batteries has similar working mechanisms as lithium-ion batteries, but sodium ions are larger than lithium ions, which make searching for the suitable electrode materials for sodium-ion batteries more difficult. But nevertheless, because we have abundant sodium source on Earth and the price is cheap, so we think that sodium-ion batteries are promising, especially for this large-scale energy storage in the future. So that we are interested in this electrode materials for sodium-ion batteries. So for the electrode materials, the layered transition metal oxides are promising cathode materials for sodium-ion batteries. So especially we are interested in this sodium manganese oxide, so which has a high theoretical capacity, about 243 milliampere hour per gram. And there are several different layered structures for this sodium manganese oxide, like the O3 type, P2 type, and monoclinic. And for all these layered structures, they have a limited interlayer spacing from like 5 angstrom to 6 angstrom, so which actually limits the sodium diffusion in the interlayer. And also when we look at the when we look at this charge discharge profiles for this monoclinic sodium manganese oxide, we can see many voltage plateaus and during charge and discharge, indicating many phase transitions during the cycling. And we can see a fast capacity fading during the cycling. So indicates this layer structure are not stable. And then we notice that there is another type of layered structure, which is called Burnside. For the Burnside structure, we have the crystal water exist at the interlayer, which can expand the interlayer spacing. And for the Burnside, it has the largest interlayer distance of about 0.7 nanometers. And for the Burnside structure, it has some advantages. So first, it can reduce the charge screening effect. And also it can help improve the sodium ion diffusion in the interlayer. When we compare this layered structure with and without crystal water, we can find that this Burnside structure can have a larger specific capacity and improve the cycle performance. But however, the crystal water also has some disadvantage. We know that at the interlayer, the sodium ions and the crystal water will compete to occupy the interlayer position. So if we have too much crystal water, the sodium content will be very low. So in the previous work for this Burnside, usually we have a very low sodium content, and the sodium to manganese ratio is usually about 0.3 or 0.4, and the highest value is about 0.7 in the previous work. So if the sodium content is low, this layered structure actually is not very stable, especially at the charge state. It is similar to lithium copper oxide. If we take all lithium out, this copper oxide is not stable at charge state. So this is the problem. For this work, we're trying to design ideal layered structure for based on the Burnside structure for sodium storage. So first, we will need a high sodium content to increase the capacity, and then we will need the large interlayer distance to enable a fast sodium ion diffusion. And we also need to reduce the crystal water content, because there is a trade-off between the high sodium content and the crystal water content. If we have too much crystal water, we cannot increase the sodium content. And finally, because this Burnside is still a semiconductor materials, if we can further increase the electron transport, which will make it ideal layered structure for the reversible sodium interconnection and the de-interconnection. So this is our design idea. And then we are trying to find some synthesis methods to prepare such high sodium content Burnside. So in one of our previous work, we used this electrochemical oxidation, which can convert the spinel MM304 to the sodium Burnside. And by using this method, we can obtain a high sodium content Burnside, which has a sodium to manganese ratio of about 0.5. And by using this high sodium content Burnside, we can extend its potential window in the aqueous electrolyte. And by using this sodium Burnside, we successfully constructed a 2.6 volt asymmetric supercapacitor in aqueous electrolyte. So by extending this voltage window, we successfully increase the energy density to about 8 watt-hour per kilogram for this supercapacitor. But nevertheless, this method is still not efficient enough to obtain a high sodium content. So in another work, we used this hydrothermalization to convert the spinel MM304 to the spinel lithium manganese oxide. Then we start to think if we can use a similar hydrothermal sodiation method to prepare this layered sodium manganese oxide with a high sodium content. Then we tried this hydrothermal sodiation, and we find that this actually is a very effective method, and we can manipulate the sodium and crystal water content at the interlayer. We prepared the different samples from S1 to S3 with increasing sodium content and decreasing crystal water content. And finally, we can get a very high sodium content with a sodium to manganese ratio equal to 1. And for this high sodium content sample, S3, we further anneal it in the argon atmosphere to remove all the crystal water. So from this TGA result, we can see that for S4 sample, there is no crystal water at the interlayer. Then we find an interesting phenomenon. because for the traditional Burnside structure, if we heat it and remove the crystal water, the interlayer distance will decrease from 0.7 nanometer to about 0.5 nanometer, which where loss is large interlayer distance advantage. But for the Burnside structure we prepared in the present study, we find that this interlayer distance doesn't change much after we remove all the crystal water. It can still be retained at around 0.7 nanometer. So this phenomenon indicates that this Burnside structure should be different from the traditional one. So after that, we try to figure out why. What is the difference? So first, we're looking at the morphology for this sodium Burnside. So we can see this material has normal the morphology for the Burnside. The material is composed of this ultra thin nylon sheets, and from this oxygen X-ray absorption near edge spectra, we can see that for the S4 sample, this oxygen pre-peak is greatly reduced as compared to the S3 sample, which indicates that we successfully induce the oxygen vacancy in this material by heating it in the eigen atmosphere. So this can actually improve the electron transfer in this material. And from the XPS result, we speculate there probably exists this manganese-oxygen hydrogen bond at the interlayer. And we think this may be maybe stabilize this layered structure when we remove all the crystal water. After that, we look at the atomic structure. And when we look at the atomic structure, it is very interesting that we can find two types of atomic arrangements. So first we look at from this 001 direction, and we can find two types of atomic arrangements. For figure C, this is the atomic arrangements according to the normal O'3 layered structure. However, for this figure B, this atomic arrangements has never been reported in previous work. And from this 010 direction, they all look the same. So based on this atomic arrangements from different directions, we construct the structure model for this new phase, which we call it as H'3 phase, because this new phase is composed by this manganese oxygen hydrogen hexahedron, but not the normally manganese oxygen octahedron. So which means we actually find a new layered polymorph in this Burnside structure, and we think this new phase is the key that can stabilize this layered structure when we remove all the crystal water, and it can retain a large interlayer distance. Then after that, we look at the electrochemical performance. So we find that this Burnside has a large specific capacitance. For the S4 sample, the reversible specific capacity can reach above 200 milliampere hour per gram. And for the S4 sample, it also exhibits very good rate performance and cycle performance. So for the S4 sample, at high rate, about 50 C, the electrode still can deliver 156 milliampere hour per gram. And after 1,000 cycles, this S4 electrode still can retain 94% of the capacity retention. And this cycle performance outperforms the previously reported O3 type or P2 type sodium manganese oxide. So which indicates that this layer structure is highly stable. And it can have very fast sodium diffusion at the interlayer. So after that, we trying to investigate the structure evolution during the charge and the discharge. So we did this in situ synchrotron XRD, and we can find during the charge and the discharge, this material has no phase transition, and the volume change during this charge and discharge is only 2%. So which indicates the structure is highly stable during the charge discharge because the volume change is very small. And I mean, the strain during the charge discharge should also be very small because the small volume change. And we also did this STEM Hardif image for this full solidation state and full dissolution state. So we can see actually this structure has negligible change between the charge and the discharge. And especially for this interlayer distance, we can see it only changes slightly between this full solidation state and the full dissolution state. Then after that, we further did the XRD and SEM. For the sample, we can find that this layered structure is well retained after thousands of cycles, and even the morphology is also well retained after the cycling. So further demonstrates that this layered structure with large interlayer spacing is highly stable and for reversible sodium interconnection and the de-interconnection. Okay, so finally, well, there's the conclusion part. So first, for this layered structure, expanding the interlayer spacing can effectively improve the electrochemical performance. And for this Burnside, we need high sodium content and low crystal water content to achieve a high capacity and good structure stability. And for this, in this material, this new polymorph with this manganese, oxygen, hydrogen, hexahedron plays an important role in expanding the interlayer of the Burnside when removing all this crystal water. Okay, so finally is the acknowledgements. I would like to thank my students and colleagues who contributed to this work, and also the funding support. And okay, that's all. Thanks for your time and attention.